what we want to do here for the next, say, 20 minutes, you'll be given the graph of a function without giving you the equation involved. From these properties you have learned so far, the curvature, the inflection point, derivative, and the interpretation of these things, you will be able to draw the graph of the first derivative and the second derivative. For example, if you were given y equals x minus 2, x minus 5, you know it's going to be a minimum which crosses at 2 and 5. Okay? The turning points will be somewhere. I'm not saying exactly on 0. Maybe, I don't know. Okay? The first derivative of x squared minus 7x plus 10 will be 2x minus 7. Right? Which means it passes through minus 7 and it's a positive gradient. So I have something like that. Okay? Then also, the second derivative will be 2. So the second derivative will be that. But we're able to do this because we know what the equation looks like. In this question and this question, we don't know what the equation looks like. But we have the graph of f of x. We're interested in what will be the graph of the first derivative and the second derivative. So let's observe. First, I'd like to remind us of this. If f of x is greater than or equal to 0, you have an increasing function in that interval. If you have less than 0, you have a decreasing function. F of x greater than 0 means the gradient is positive. If your gradient is positive, that's an increasing function, right? If your gradient is negative, that's a decreasing function. At this point where this happens, you have a point of inflection, which is also a stationary point, right? So we call it stationary inflection point, or a stationary point of inflection. And if you have this, but this holds, you have a point of inflection, but non-stationary. So we call that a non-stationary point of inflection. Those are the ones that come like that, right? The stationary ones are the ones that goes like so. It's coming down, then it goes back. So that's the stationary point of inflection. Understand? If this happens, you talk about concave up, which is responsible for the minimum point. If it's concave up, then you have, oh, there's a minimum point, if that shape is concave up. If the shape is concave down, then you have, oh, maximum point. So these two represent this. Now, at this point, if this happens at that point of inflection, then we say there's a change in the shape of the curve. At the point of inflection, that's where the curvature changes. That's the purpose of investigating second derivative. Okay? And finally, just to remind ourselves that this is the rate of change of the function f, while the second derivative is the rate of change of the gradient. Just a reminder. Okay, for this, we are interested in the first derivative first, then second derivative. Clearly, this is a cubic function. So our first derivative will be a quadratic function. Is that not? But for us to get a quadratic function, we need some things. A quadratic function, we have a minimum or a maximum point. We don't know. Is that not? At the local minimum and maximum, dy dx is equal to 0. Is that not? Anyways, now, we can see turning point. First, locate your critical point. This is a critical point. This is another critical point. Okay? At this point, if I call this A and I call this B, okay, A and B are local maximum and minimum points. Okay? At A and B, where at this point the first derivative is equal to 0. Do you agree? Now, when you say y is equal to 0, that's where it crosses x-axis. Remember, when you say f of x is equal to 0, we are saying where f of x meets y is equal to 0, which is the x-axis. So similarly, when you say this is equal to 0, we are saying when the first derivative crosses the x-axis. The implication of that is that the graph you are looking for crosses the x-axis at these 2 points. Again, f of x equals 0 means where this graph of f of x crosses the x-axis. So when you say something equal to 0, you are saying when that equation crosses the x-axis. So similarly, when f prime of x is equal to 0, we are saying when the graph of f prime of x crosses the x-axis. And if this turning point is where we get this equation, we are saying the values of x here are responsible for where it crosses the x-axis. So now, does it cross this way or does it go that way? We don't know yet. Am I making sense? Now, again, here is a stationary point, clearly. That's where the curvature changes, right? So this is another interesting point. At this point, oh, we don't even need to talk about that yet, because that is when the second derivative is equal to 0. Is that not? So it means our second derivative will pass through that point, clearly. So, but we don't need to talk about that yet. Now, to know our minimum or maximum, whether our first derivative is of minimum or of maximum, let's see what can we do. Let us go to the sign diagram to see how this curve behaves. Now, about the critical points. About the critical points, A and B. Before A, we are interested in this, right? Before A, the gradient is positive. You agree? Right? Mm-hmm. In between A and B, the gradient is negative. And after B, the gradient is positive. Which means when I draw the graph of function of x, between here must be above the y-axis. In between here must be below the y-axis. Understand? And here also above the y-axis. So clearly it's going to go this way. Am I making sense? Then one last point. This point, let's call that C. At C, we know that that is equal to 0. Okay? This means something. It means the derivative of the first derivative is equal to 0. Is that not? Which means this point is a stationary point for the curve representing the first derivative. Okay. When you say f prime of x is equal to 0, you are talking about the stationary point of f of x. Is that not? So now, you are talking about the derivative of the first derivative. What is the meaning of dy dx is equal to 0? At the stationary point, dy by dx is equal to 0 means at the station you are interested, you are talking about y equals f of x in that case. Are you with me? If your graph is y, dy by dx is equal to 0 means for this curve, at this point when I get the derivative of this to be 0, is where this curve y turns. Whether it turns above or below, we don't care. We're not talking about that now. But that's where it turns. So this fact can be used for two things. Apart from the point of inflection, it's also the stationary point of the first derivative. So this means that this has stationary points at where? At C. The curve we are interested in turns at C at x is equal to 0, which is at C. So we already know that cross is here. We know that from at this point it's going to be above. At this point it's going to be above. Clearly it's going to go in like this. Now we know the turning point is when x is equal to 0. So our curve is going to go this way. So it's going to turn along the y-axis. Understand that? So it's going to go like this. That's what we are saying. So this is the graph of the first derivative. Understand? Then the graph of second derivative is easier. Clue number one. It will definitely be a line. It will definitely, because this is a quadratic, right? Then the next one is a linear. At the point of inflection, what happens? Second derivative is 0. So the graph you are looking for crosses the x-axis at the point of inflection. That is the implication of this. Remember, y equals 0 means where y crosses the x-axis. This equals 0 means where f prime of x crosses the x-axis. Similarly, this equals to 0 means where the second derivative, the graph of the second derivative crosses the x-axis. So your second derivative crosses here. The question is, was it coming this way to cross, or was it coming this way to cross? Then you can go to the line diagram again. Now we are talking about the point C, yes? Before the point C, what is the gradient looking like? You are looking at the rate of change of the gradient. This is what? Is it increasing? The gradient is increasing, isn't it? Do you understand that? Or let's look at it this way. Yes, you have a negative gradient. Is that not? Negative gradient here, positive gradient here. Okay? So which means from this point you have below, from this point you have above. Do you understand that? So our last line will go this way. Let's say this. Hope I have not missed anything out. So this will be the graph of the second derivative. No. Also, you can look at it with curvature, from curvature point of view. From here, what happens to the graph? You can also look at it that way. Remember, it's concave downward. Here. Concave down. I'm looking at the black line now. Between this range, you have concave down. Look at the black curve. Okay? Concave down. Concave down is when you have this. That's when you have your local maximum. Okay? So concave down means f second derivative is less than 0, which means every part of the second derivative is below the y-axis. Are you listening, miss? Concave up means when your second derivative is greater than or equal to 0, which means the graph you are interested in is above the y-axis, above the x-axis, sorry. So you can see from here, the pink line or whatever, orange, is above. And at this point is below. Does it make sense? We have 7 more minutes. Let's look at the second one here. Wait. What? Oh, I'm so sorry. I was looking at the 10:45 period. I am so sorry. Please go for your lesson. I thought it's what? I'm so sorry. I see why Brand